Hi guys, so a short video with only two problems here that you kind of the problem that you can have for the MCAT. So here they are showing you an experiment that is done in the lab. They are using monochromatic light. So here we have, that's going to be the wavelength, nanometers. It's a yellow light. And they are trying different material here to compute the critical angle. Okay, so you go from slow, which is like the material here, the medium, to fast. And as you increase the incident angle at some point, you're going to reach the critical angle. And beyond that, the light will be totally reflected. You have total reflection and the light is trapped inside. So first of all, this half disk here will behave like a converging lens. You see, because it's thicker at the center and thinner at the edge. So that will be like a converging lens. Second of all, let's just quickly review the critical angle. Critical angle only happens when you go from slow to fast. So from a larger index of refraction to a smaller index of refraction. So you see here, you do have refraction, and as you increase the angle of incidence, the angle here is going to increase as well, following the thin lens equation. And then at some point, the angle of refraction is going to be 90 degrees. 90 degrees here. When you get to 90 degrees, that's going to be the critical angle, right? So if you have water, for example, the critical angle is going to be about 40 something, 48. See, that is 40, 45. So that's going to be 48 degrees. That's going to be the critical angle. And anything beyond that, it's going to be totally reflected. So it's a total reflection. Now, if here you increase the index, here you go, for example, somewhere there, you see that you're going to have less refraction and that the critical angle is going to increase. Okay, so when you have less contrast between medium 1 and medium 2, even though this one has a larger index of refraction, you can still have total reflection, but the critical angle will be larger, okay, about 60. Here, when you go from water to thick air, whatever it is. Okay, so let's look at the question. So let's see, number one. Number one is tricky because they talk about flint glass. And if you go to here, you see flint glass critical angle is 38 degrees. So right away, you want to jump on that answer. But it says here, yellow light goes from air to glass. So you go from fast to slow. So it's not total reflection. The light will escape. So in that case, we're talking about from fast. So we go from fast to slow. So there is no critical angle, okay? So that means it can escape, right? So we have an angle of 60 degrees. The angle of refraction will be smaller than 60. So here it says 40. So the only two answers that are possible will be 32 and 38, either one. But 38 here should match with 90 degrees. So it means if, because of the symmetry, if the angle here is 90 degrees, then the refraction angle will be 38. Okay? Because here, for example, if I go to 90 degrees, let's say you take water, let's take water exactly. So if I go to, if the incidence angle is 90 degrees, the refraction here, the angle of refraction will be about 40, 45, 48 degrees. Okay, and 48 degrees is the critical angle for water. So if you have 60, if it's 60, it has to be smaller than the angle, the critical angle. So it should be 32. Okay. So you see here when the incidence, if you take the example of water, if the incidence here is 90 degrees, I'm going to get 48 here. Because there is a symmetry. If I go from water here, if I go from water to air, you see that the angle, the critical angle, it goes to 48, and the 48, and the refraction will be 90. So 90 has to match with the critical angle. So since you have 38 here, that will be an angle of refraction. That means the incidence angle has to be 90 and not 60. So the right answer will be 32. Okay, number 2. So the focal point closest to the lens. So if you remember from the lecture, here when you have a lens, if you increase the refraction power of the lens, if the lens is more refractive, you see that the focal point get closer to the lens, right? So if you make the lens thicker, or if you increase the density of the material, the lens becomes more refractive. And if you decrease the refractive power of the lens, the focal length is larger. The focal point is moving away from the lens. So we need to find which of those material is the most refractive. And the most refractive will be the material with the smallest critical angle, 22.4. Okay, so smaller the critical angle is, that means the smaller the focal length is, because you get more refraction. Again, you can play. I highly recommend that you play with this app. You see that if I increase the density of the material, then the critical angle, it's going to get smaller, right? Instead of having 48, now I have like 40. This is 35, 40, not even, right? I have like 38 degrees. Where am I? Here. Okay, so which one has the smaller critical angle? So that will be that material here, which is answer is C. Okay, so we want to do that experiment, which is finding the critical angle. We want a material that is transparent to visible light, uniform composition, uniform temperature, and that's not correct here. So the answer will be D. You don't want a material that absorbs yellow light, because then there is no more experiment, right? So monochromatic light means it's one wavelength, and we don't worry about diffraction. Complication caused by diffraction? No, diffraction happens. There is no problem with diffraction. Monochromatic light complication caused by dispersion. So dispersion happens when you have white light that will split in with the different colors of the rainbow. So that's a problem. Reflection, no, we don't worry about reflection here. So that will be 2. So the 4 is B. So it's going to be B only, right? Because remember, when you have a prism here, if you take white light, then of course you're going to make a rainbow. If you take a prism, here is a rainbow. So it's called dispersion. And if you increase the index here of refraction, it's going to disperse even more. Okay, so the red will move further away from the blue. If there is less, if you go from that medium to water, you're going to have less dispersion. So anyway, if instead of having white light, you just have red or blue, you see you don't have to worry about dispersion. There is no dispersion. Okay, so that's for number 4. So if you put light from point A, so point A is here. If you put the light here, you see there won't be any refraction. It's going to go in a straight line and it's going to hit the screen here. So I recommend that you pause the video and try to solve the problems, of course, but it will go in a straight line, and you can see that here again. If I take my half circle and if I try to go straight, more or less, you see it go in a straight line and it doesn't bend. There is no bending of light. So this one is tricky. Okay, so you want to look at the answers and think about it. So if you have this same experiment, but now you place that lens inside water, instead of air. So if you have water and not air, you still go from slower to faster. Okay, so this is more dense than water, but now you have less contrast. Okay, there is less contrast between the index of refraction. So here, index of refraction was 1. Instead of 1, you're going to have 1.33. Okay, so that means the critical angle will be larger, okay, because it's not refracted as much. Okay, so I can show you that here. If you, so here you have whatever it is here, you see the angle of the critical angle is about 38, almost 40 degrees. But now in here, if I have less contrast in the density for the two materials here, if I put water here, you see that the critical angle will be way larger, right? So now instead of 38, I'm gonna have something like almost 60, right? Maybe 55, maybe 55. So there is less contrast. Also, so the critical angle will be smaller, and you see when it escapes here, the angle of refraction will be smaller as well. See if I put air here, So you have more refraction. And if I put water, you have less refraction. So the critical angle will be larger and the angle of refraction will be smaller. So if you have less contrast, less contrast, between those two materials, the critical angle will be larger, and the angle of refraction will be smaller. So if I go back to air, I get smaller. So the answer is the critical angle will be greater and the angle of refraction will be smaller. So it's just that you can explain that by the contrast between those two media. And you really have to play with that to really understand really well. And then you can ace those questions. Okay, so I hope that was not too confusing. Number 7, they talk about mirror now. And remember, when you have a plane mirror, so let's look at mirrors now. Let's go back to mirrors. Where are my mirrors? Here. So if you have a plane mirror, so you see the distance here between the object and the virtual image is the same. You always get a virtual image which is the same size of the object. Second of all, something to remember, if you want to have, if you have a person, if there is someone here, and looking in the mirror, and we discussed that in the lecture, if you want to see the full body, all you need is a mirror which is half the height of the person or bigger. So if I call that h, and this is the height of the person, I want a mirror to be equals or larger than h over 2. So if I have half of the size of the person, I will be able to see the whole person, or the person will be able to see himself or herself in the mirror, right? Because here light will be back and fit more like this. So we see the image. Beyond the mirror, of course, right? So here the mirror is 1 meter. So you can see a person who is 1 meter. So 1 meter, that's going to work. If a person is 2 meters high and the mirror is half, that's going to work. If the person is 0.5, of course it's going to work because it's twice as big. But if the person is 4 meters, that's not going to work because you need a mirror which is at least 2 meters. Okay? Well, yeah, here. So spherical convex mirror and plane mirror. So convex mirror, they are actually these are convex mirror and they are diverging mirror, and you see that the image is always virtual, is always smaller and it's always beyond, right? Behind the mirror. And if I put the object really far away, the image will be here at the focal point and it's going to be smaller. So let's look at the answer. Both mirror only virtual image. Yes, that's true. Smaller, this is true for the spherical mirror, but it's not true for the plane mirror. Both mirror form image that are closer to the mirror than the object. That's true for the spherical mirror. You see the object here is close relative to this distance, but that's not true for the plane mirror because in that case, those distances here are exactly the same. So the only answer is A. So I have a concave mirror now. And you are given a distance from its surface that is 3 times the mirror focal length. So now you have a concave mirror, which is a converging mirror. Okay, so this is the focal distance. This is twice the focal distance. Twice the focal distance is the radius of the mirror, right? It has a curvature here, and if you extend, make a circle, that's going to be the radius of the mirror. In that case, you see the image and the object have exactly the same size. The image is real, can be displayed on the screen. It's upside down and they have both the same size if the object is placed as at that distance here, which is twice the focal distance. Then if I move the object further away, which is about 3 times the focal distance, you have a real image in front of the mirror and it's going to be upside down. In that case, it's going to be smaller. And you want to find you want to apply the equation is the same for the lenses. So if you have 3, so 1 over 3f, that's the distance for the object, plus 1 over I equals 1 over f. So you solve for I, which is 1 over f minus 3. That's going to be a 3, that's going to be a 3, that's going to be 2 over 3f. So I equals 3f over 2. And so the answer is A. Right, it has to be in front of the mirror, and that's going to be the answer here. So if you place the object at a distance 1 to 3 times the focal distance, the object will be here at about 1.5, the focal distance. So spherical mirror, the light color component. So here they talk about the frequency, but mirrors deal with reflection, and reflection have nothing to do with the frequency, right? Frequency, we worry about that when we are dealing with refraction, but here we are dealing with reflection, so we don't worry about the frequency. So the answer is A. Okay, so if you place a mirror and a lens in water, so you're going to change definitively the refraction for the lens because there will be more contrast, right? If you have lens which is in air, you have more contrast between the index of refraction, and in water you have less contrast. So it will be less refractive when you place it in water. So the focal length will be decreasing if you place, the focal length will be increasing, sorry, right? So if you have your lens, if you have the lens here, and if you make it less refractive, you see that the focal length is moving away from the lens, so it's increasing. If you make it more refractive, so more refractive power, the focal length is decreasing. So if you place a lens inside the water, the focal length of the lens will increase. The mirror doesn't care about refraction. So the answer is 12C. Let me check. 12C, yes. 12C. Okay, so remember that if there is a contrast here and less contrast, then there will be less refraction. Even if you go from, for example, if you go from water to glass, you go from fast to slow, see there is less refraction relative to, for example, if you go from air. So here you have more refraction, that means that angle will be smaller relative to this situation here. So if you have less contrast between the lens and the outside of the lens, you're going to have less refraction. It doesn't bend. It's not going to bend as much. Okay, that's it for today.